Hi, this is Mrs. Clark, and this is my video on the segment addition postulate. So this paper you're going to fold in half, and you're going to glue onto your notebook page. It's going to be a little book. And we're going to look at segment addition on the front page, and then we'll do a couple different things on the inside. This video will be in parts, so make sure that you are watching the part that you need, whether it's the first page, the second page, or the third page. Alright. So at the beginning it talks about postulates. Postulates are things that are common sense. So they have the ruler postulate, which allows us to measure with a ruler the endpoints of a segment, so we can match it up with a ruler and allow us to give the length of a segment. And then we have what's called the segment addition postulate. So we've been learning how to find the length of segments using the distance formula if we're given their coordinates, or using Pythagorean theorem if they're on the graph drawing a triangle. Or if we have a triangle and the lengths of sides, we can find the length of another side with Pythagorean theorem. Segment addition postulate is if we have none of those things. No graphs, no triangles, nothing. Just segments and some information about the segments that helps us determine lengths. So the segment addition postulate says, given 2 points A and C, a third point B lies on the line segment. So notice B is on it, not necessarily in the middle, just somewhere on it. If that is only true if the B lies on the segment, if AB plus BC equals AC. So what does that mean? Notice that this doesn't have a symbol over the top of it, so I want to point that out. When this has no symbol, that means that they're talking about the length of segment AB. So no symbol here is on purpose. It's not an accident. AB without a symbol means the length of segment AB. And so what this segment addition postulate says is, if I take AB, just this part, from A to B, from here to here, and I add to it this other part, BC, from here to here, I will get the length of AC, which is the whole thing, from here to here. That seems like a very obvious statement. If I take one piece and add it to the other piece, I'm going to get the whole thing. So that's what the segment addition postulate tells us. What it allows us to do is to use that information to create equations. So we've previously reviewed how to solve equations. You'll notice in this first example there are some algebraic expressions here. We're going to talk about how do I go from what I have here to making ourselves an algebraic equation. So first we're going to look at example 1. It says L is between J and K. So that means that they're all collinear. And if I were to draw a segment from J to K, L would be a point somewhere on it, kind of like this picture. So I'm going to draw something very similar. So I'm going to draw a J, and I'm going to draw a K, and I'm going to put L as a point on the segment somewhere, not in the middle, because it didn't say it was in the middle, so I'm going to put it purposely not in the middle. I'm going to put it over to the side over here. Then they give us some more information. They say JL is 2x minus 3, and LK is 3x plus 5. So I'm going to add that information to our diagram. So JL gets 2x minus 3, and LK gets 3x plus 5. And then JK is 42. So from here to here, the whole length of the segment is 42. So I'm going to draw these little swoopy brackets and say 42 is the whole thing from J to K. So drawing this diagram is going to be part of your communication for this problem, so it's really important to draw the diagram. The next thing we're going to look at is, what would a segment addition equation look like? So what would a segment addition postulate equation look like for this problem? Well, we would say one of the pieces, JL, if I add that to the other piece, LK, it should equal the whole piece, which is JK. So writing this letter equation is also part of your communication, so you understand how the segments are working together in this diagram. The next thing that we're going to do, though, is take this letter equation and transform it into these algebra expressions that we have written here. So JL has 2x minus 3, so instead of that, I'm going to write 2x minus 3. then that's going to be added to LK, so I'm going to put plus. Instead of LK, I'm going to put 3x plus 5, because that's the expression for LK. And equals, and then instead of JK, I'm going to put 42. Now I've built myself an algebraic equation that I can solve to figure out what x is. Why do I want to know what x is? Because down here they're asking me what is JL and what is LK. So in order to find those, I need to know x because they are these algebraic expressions that have x in them. So let's solve this equation, and then we'll find out what x is, and then I can show you how to find each of these. So to solve this equation, there's no distribution, there's no parentheses, so we're going to start by combining like terms. There's actually a bunch of like terms here. I've got 2x and 3x that can be combined together, so that makes 5x. And then I also have this minus 3 here and this plus 5 that can combine together to be 2, and because it's positive 2, I'm going to put plus 2. And then that equals 42. So I went from this long equation, combining my x's and combining my numbers, to this much shorter equation. All my variables are together over here, so I don't need to do that step. But I'm next going to look at what addition or subtraction can I do to undo. So if I'm looking at the 5x side, I have a plus 2. I'm going to try to get rid of that by subtracting 2. When I do that, I am left with just the 5x here, but 2 and minus 2 are 0, so that cancels out. So 5x is going to equal 42 minus 2, which is 40. Then I have this 5 times x. I'm going to get rid of the 5 by dividing by 5 on both sides. 5 divided by 5 is 1, so I have 1x equals 40 divided by 5, which is 8. So now I know x is 8. I've got to find the length of JL. I can do that because I know x is 8 and JL is 2x minus 3. So to find JL, it's 2x minus 3. I almost wrote a plus there, sorry. So that means I have to do 2 times 8 minus 3. 2 times 8 is 16. 16 minus 3 is 13. So JL is 13. I can do the same thing with LK to find the length of LK. So LK is 3x plus 5. So I'm going to do 3 times 8 plus 5. 3 times 8 is 24. 24 plus 5 is 29. So LK is 29. If I wanted to check to see if I was right, I would add 29 and 13 to make sure I get 42. And there you have it. That's how we use segment addition to solve for what the lengths of the two of the segments are. If I know the whole thing is 42, I use my algebra to solve that. We're going to do the same thing with number 2. If you feel confident, feel free to pause and then come back and check your work. So number 2, A is between C and T, so I'm going to draw a segment, CT. I'm going to put A between it, purposely not in the middle. I just chose the other side this time. And then I've got CA is 4x plus 6, and AT is 7x minus 6, and CT is 132. So I'm going to write my letter equation. I know CA plus AT equals CT. So that means my algebra equation is going to follow that 4x plus 6, because that's CA, plus 7x minus 6, because that's AT, equals CT, which is 132. So just like the last one, I'm going to combine my like terms first because there's no parentheses. So 4x and 7x is 11x. Then I have positive 6 and negative 6, which makes 0, so that's easy. So 11x equals 132. To solve for this one, I'm just going to divide by 11 on both sides, and I'll get x equals 12. I need to find the length of CA, so I'm going to need to put in my 12 up here with 4x plus 6. So CA equals 4 times 12 plus 6. 4 times 12 is 48. 48 plus 6 is 54. So CA is 54. AT is 7 times 12 minus 6. 7 times 12 is 84. Minus 6 is 78. AT is 78. If I wanted to check, 78 plus 54 equals 132, so I know I'm good. So there's how we use segment addition postulate to help us create equations so we can solve for the lengths of segments. I'm going to stop my video here and make a separate video for the next page on the inside. Thanks for watching.